So it's good. I will start the attendance sheet up here, guys, so make sure it filters around to you. You know how this works, right? If you're here, you check the box. So, saying, I don't think, oh, we need a date. What's today's date?
4th.
All right. If you could put the 4th up there, that would make it official. Thank you. If you want to go ahead and hit record, I will say things. Or did you already do that?
Yeah.
Oh no. It's okay. I haven't said anything we need to edit. Let's go on. I will begin with a word of prayer then. Dearly Father, we thank you for this day. Thank you for these students. We pray you bless this class, Lord. Help us to learn a little bit more about your creation together today, Lord. In your name I pray. Amen. So I should ask you if you have any questions about the homework that I've recommended. Unfortunately, I do not have my book on me at the moment, so if you have such a question, you'll have to make sure you explain it to me, because I don't have the questions memorized. You might. Yes.
Can you do number 37? I can give you my book.
Number 37, and I can borrow your book. That works for me. I'm going to close these doors because otherwise there's a steady drumbeat of hall noise, and at some point someone will be giggling, et cetera, et cetera. So let's go ahead and close them. Now that was number 37 of what? Number 37 of what section? Number 37 of what section?
Page 19.
Page 19? Okay, that works. Page number works. So number 37 on... Oh, thanks. Oh, great question. Yeah. This is something I didn't end up touching on in lecture yet, so it's a great question. So it's number 37 from page 19. So the question is, it says the speed, v, is equal to at cubed minus bt, right? Where t refers to time, it says what are the dimensions of a and b, and what are the SI units for the constants a and b, all right? So what was your, did you have a specific question about that, or you just don't know where to start? Or okay. So when we talk about dimensions, what are the dimensions? There's 7 fundamental dimensions. I mentioned this briefly, I think, the first day. Length, time, yeah, speed is a derived, speed is like not fundamental because speed is length over time. So what length, time, not velocity, velocity is derived, it's speed, mass over time, length over time. Yeah, mass is one, yeah, amount, which was a electric current, candela, like luminous intensity or something like that. Temperature, okay. But the main ones for us are just length, mass, time. All right? So for this one, the dimension, what's the dimension of v supposed to be? It's supposed to be length over time, right? Distance divided by time. So that should be the dimensions of v, right? How does dimension work? Well, the dimension of at cubed minus bt, well, let's think about it one piece at a time. So the dimension of at cubed, the way this works is it's the dimension of a times the dimension of t, t cubed. What's the dimension of t cubed? Well, that's time cubed, right? And what's this? This is the dimension of v. So the larger point I'm making here is that each thing that's added together to make the velocity has to have the dimensions of length over time. So I can look at it like one piece at a time. In particular, the at cubed piece has to have dimensions length over time, right? But that means that whatever dimensions a has, that times time cubed has to give me length over time, right? So I do algebra. This gives me that the dimensions of a are equal to length over time times time cubed. So therefore, the dimensions of a are length times time squared. Now, I briefly mentioned, I think, the first lecture, you can't add apples and oranges. That was like the extension of that idea is that when we have a formula for velocity, each piece in the formula has to separately have the dimensions of, the derived dimensions of velocity, length over time. By the way, so I often don't think in terms of length and time squared. Personally, I usually think in SI units. Like if I'm checking dimensionality of an equation, I think in SI units. That's what I usually do. So when I think about this, if I want to think about dimensionality, I think, well, velocity has got like meters per second, right? And so we're looking at like A times something with seconds cubed minus B times something with seconds. So this is, and I say equals, but I really shouldn't say equals here because we're not saying that these are equals. We're saying that the units match up. So like this unit is equal to that unit is equal to that unit is, the math is kind of sketchy here. It's not quite regular algebra. We're just like making sure we have the same kind of things. Anyway, long story short, what would the SI units for A have to be? Yeah, you said meters second squared, right? Meters times second squared would be the SI units for A. How about B? So this over here would be whatever the SI units or whatever the dimensions are for B times the second, right? So that's meters per second. So anyway, the SI units for, I'm sorry about my notation here. It's not great, but neither is your books on this point. Yeah.
So for the A, I don't think that was the answer in the back of the book, but B, what was that?
It's not length. Oh, I bet I made an algebra mistake. Can you tell me what it was?
L over T to the fourth.
I know. Can you tell me where my algebra mistake is, though? Oh. I agree that the book is right and I'm wrong. Why am I wrong? Can you tell me where I went wrong? This arrow is very suspicious right here. See, I had, and I think I know why I meant yes? Yes, I should divide by t cubed. And see, I tricked myself into thinking that I had division by t cubed here. But this is not division by t cubed, right? I'm labeling this as t cubed. So I have to divide the equation by t cubed, which means this is supposed to be t times t cubed, right? Not this up here. And so that, of course, gives us length over t to the fourth. So, yeah. So, yes, there's no calculus in this class, but there is a truckload of algebra, right? There's a lot of algebra in physics. Unavoidable. All right? Yep.
So then the SI units would be meters.
Meters over seconds to the fourth would be the SI units here. And so or what would the dimensions be here? Or length divided by time squared. So I'm being sloppy. I'm using this bracket notation both for dimensions and for the SI units, right? SI units is a specific choice of a standard quantity of that dimension, right? Like once you make a system of measurement, we trade length for what? Like there's a standard length, the length of a meter, right? Or there's a standard time, the length of a second. How is a second defined? If you look it up, it's kind of horrible. It's got something to do with the atomic blah, 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 blah of a cesium atom or some such nonsense. It's like, ugh. Can't it just be defined like, in terms of the motion of the moon or something? Well, it used to be, but not so much anymore. We use various, atomic things to define these things as accurately as possible. All right. Another question? Yeah.
Number 16 on page 43.
Number 16 on page 43. I will unfortunately steal your book. Ooh, I like your book. Let's see here. Number 16 on page 43. So here we have an automobile traveling 95 kilometers per hour overtakes a 1.3 kilometer long train traveling the same direction on a track parallel to the road. All right, so here's a picture. Train, 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 da-da-da-da, train. And this is a very long train. How long is it? Yeah, 1.3 kilometers. That's a pretty long train. And so then there's a car, right? Do, 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 do. And as you can see, my cars are very sad. And that car is doing what? It's traveling with a velocity of 95 kilometers per hour. It says the train's speed is 75 kilometers per hour, right? The question is, how long does it take the car to pass the train, and how far will the car have traveled during this time? And then it says, what if the train was going the opposite direction to the car, right? Yeah. So how should we solve this? Have you ever, I mean, surely, so like, I don't know, once upon a time I was a teenager, I was in like a road trip, and you know, most of the cars, they just look like they're sitting next to you, right? Because they're just following the speed limit, driving along. It looks like they're stopped, right? If you just don't pay attention to the fact you're moving down the road 70 miles an hour. Then all of a sudden, out of the corner of my eye, I see this red car pull up, they look at us, and then proceed to pull away, you know? So, I mean, by the time they're out of sight, I guess the Ferrari was going like 130 or something, right? So what you need to look like you're moving relative to something that's already moving is excess speed, right? I mean, I like to see, I mean, I personally admire speeders. If I see somebody go past me at a high rate of speed, I feel mad respect, you know? It's true. I don't have the money to spend on that speeding, but I respect those who do, you know? I'll admit it. And I must say that most of the speed limit signs we have in this country are wrong. I mean, just look at traffic, right? Just saying. Do I need to explain that joke? No? Okay, all right. Okay, so the idea here is relative velocity. What's the relative velocity of the car to the train? How fast is the car going relative to the train? 20, yeah, right. If you can imagine yourself riding on the train, it would appear as if that car was going 20 miles per hour past you, right? So the relative speed is v car equals to 20 kilometers per hour with respect to train. Okay? And so then I want to figure out what's the relation between, now it's constant velocity, right? We don't have any acceleration, so we get to use our beloved constant velocity formulas, which is what? V car equals change in x over change in t. Generically speaking, that's the formula for average velocity, right? Now, we don't know what the change in time is. We're asked that. How long does it take for the car to overtake the train, right? What is the change in x? How far is, what's the length of the train, right? So, again, we should do algebra. This says that delta t, hopefully I'll get it right this time, is the velocity of the car divided by the, well, length of the train, right? Which is then what? 20 kilometers per hour divided by, what we got? Length of train, 1.3. This feels wrong. Guys, all right, very good. You guys got me. All right, I made a mistake. On purpose, of course. Now, I don't know. Was that on purpose? But it serves a purpose. We can tell that I did an algebra mistake. How? Yeah, the units don't work out, and also you guys have algebra sense, so you know that I did something wrong, right? Both of those are good reasons. But yeah, the units don't work out. I got units of 1 over hours. That's no bueno. So, I shouldn't. Those erasers are miserable. All right, let me see if I can do the math right this time. So what we got? Delta t is equal to the velocity. Did I do the same thing again? I'm sorry, guys. I hiked over to Walmart right before right before class starting at this building. I'm a little bit off. Fortunately, my wife came and drove me back, which is good. Otherwise, but I knew I had just enough time to get these silly hang-up strips, so I was like, all right, fine. Anyway, I promise I won't walk to Walmart right before class in 90-degree heat again. So I hopefully will be slightly more cogent like Thursday. All right, anyway. Getting to the point. 1.3 kilometers divided by what? Divided by 20 kilometers per hour. Yay, units, much better. And then what's 1.3 over 20? What's that? I didn't hear you guys. 0.065? 0.065? 0.625? There's another 0. All right. 0.0625 kilometers. Hours. 65. You guys are trying to make me pick up my calculator, aren't you? You have your wish here pretty soon. So there you go. That's not too long, is it? How long is that? About 5 minutes or so? Something like, I don't know exactly. Okay. What else were we asked? I've forgotten now. So how would we answer that? How far has the car traveled? Now, what is that saying? That's asking how far the car has traveled with respect to the frame of reference of the ground. Right? So how fast is the car going with respect to the ground? What's that? 95. Right. So to find the distance traveled by car, we're going to do, let's see here, 95 kilometers per hour times the time, which we just figured out is 0.065 hours. Whatever that works out to. All right. 6.175? All right. Kilometers. See, because the hours cancel this time, right? Now, conceptually, what would happen if the situation was reversed? What if the train's coming at the car? The magnitudes of the velocities are the same, but the directions are so that, the train and the car are going towards a head-on, collision course, but not actually a collision, they're driving past each other, right? I mean, usually you don't have a trouble of going down the highway and going, oh no, there's like a train coming in the opposite direction and I can't avoid it, right? That would be like an action movie, not actually real life, right? Have we had an action movie with a full-size 1.3 kilometer train going down a highway? Has that been done yet? And are any of you theater majors? Cinematic arts? No? Hey, don't they need physics? Come on. All right, never mind. There's nothing to learn here. Do you understand how to do the other way? So the other way, the relative speed of the car and the train would be 75 plus 95, which would be 170 kilometers per hour. So it would take less time, right? And the car would travel less time as well. Do I need to write that out, or do you get the idea now? Okay. There's another similar problem I often cover. I'm fond of this problem because it's really hard to work with anything but the average velocity concept. Like even when I teach the calculus-based physics, this question requires the stuff you guys learn in here. And it's a fun question. You imagine two trains on a collision course, and then you imagine like Superman flying back and forth between the trains, right? Like he's trying to have a conversation with, let's say Lois is in one of the conducting cars and the other one's got Jimmy, and he's like playing a game of telephone, talking, like giving they don't have cell phones because for the purposes of this illustration. And Superman's got to like say, okay, and also the purpose of this communication, the conversations are very, very short. So actually, let's say it's like, I don't know, you make up your favorite interaction between Lois and Jimmy, the point is Superman's got to fly back and forth between these two trains on a head-on collision. And the question is, if the trains are going at each other both with a speed of 60 miles per hour, and they're 100 miles apart, and Superman is just flying back and forth between the trains at, how fast does Superman go? What's that? 1,000 miles an hour, let's say, right? Then how far does Superman fly during this time? Ignoring the time for turnaround. He's Superman. It takes him no time to reverse direction. He's just flying back and forth between these trains, bop, 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 for, until they come together after an hour. So how far would a Superman gone in this situation? Let me draw a picture. I mean, you're not going to find a formula for this in your book, are you? You got to use concept. So this is the one train. Let's say train Jimmy, 60 miles an hour. And then over here you got train, how do we spell Lois? I don't know. L-O-I-S, all right, very good. And just to keep it interesting, we'll make that go 40 miles an hour. All right? So, and then you got Superman. And to start with, they're how far apart? Let's say 100 miles. Keep it simple. And then you got Superman flying 1,000 miles an hour back and forth, right? Superman, 1,000 miles an hour. He starts here, and then he goes over here. Says, "Hi, Lois, what's up?" And he goes back here, and says, "Hi, Jimmy, what's going on?" And then back here, and then back here, and then back here, and back here. And then eventually these trains come together somewhere in the middle, at which point the process stops. How far did Superman fly? If he's always, because he's flying shorter and shorter trips each time, right? Because the trains are approaching, How far did Superman fly in this process? How would you do it? Any ideas? So, how long does Superman have to fly is the question, really. 100 miles? No, see, this is an unfortunate thing about English. When we say how long, what does that mean? It has two meanings, doesn't it? Sometimes it means actual length, but our usage of that term also has, it's like point, counterpoint. Let's see here. You guys, these squeaky chairs distracted me, easily distracted. Anyway, so how long, when I just used it in the sense of time. How much time, how long in time does it take for them to come together? An hour, why is that? How'd you know that? Right, so that is right, and not wrong, but like the concept you're using is relative velocity, whether you realize it or not. Like that's behind your intuition is the concept of relative velocity. So relative to each other, they're going 100 miles an hour. If I was to put myself in the Jimmy train frame of reference and ask how fast is train Lois going, the answer is 100 miles an hour at me. So the relative speed is 100 miles an hour. So you're absolutely right. After 1 hour, they together have traveled 100 miles and they're going to be at the meeting point. So the delta t is 1 hour. And once you figure that out, you know that Superman is flying 1,000 miles an hour. So Superman flew how far? 1,000 miles, because he was flying an average speed of 1,000 miles an hour for an hour.
Wait, back up to where you were talking about the hours.
Yeah.
So how did you determine that?
We determined that because the delta x was equal to 100 miles. And the velocity of the relative velocity of trains was 100 miles per hour. And then so how's it go? V is equal to delta x over delta t. So delta t is equal to delta x over v, which in this case was 100 miles divided by 100 miles per hour, which is equal to 1 hour. You're really good at algebra. You did all that algebra in your head, right? Exactly. You used common sense, my old nemesis in physics grading. Right? It's hard to see that. That's fine, not wrong, good in fact. But the trouble is for us with certain problems, if your common sense is wrong, and you just write down common sense answer on the test, then it's hard for me to give common credit. I mean, partial credit, you know. So I don't want to discourage you from using common sense. I mean, I think we should all use common sense, right? But anyway. We should also use the equations of physics and try to show our work. So anyway, that's a very popular question. Do you guys have another question for me while I erase the board? Yep. Number 35 of chapter 2. And I'm sorry I don't have a quiz prepared for you guys. I'll get with it eventually here. It's okay. A runner hopes to complete the 10,000. Whoa. Really? 10,000 meter run in less than 30 minutes? Really? I think this is a runner that maybe only exists in physics books. Did I do it wrong? Oh, 10,000 meter. I guess that's just 10 kilometers. Oh, that's not too bad, is it? I don't know. I have a, so it's, so you're, so I certainly couldn't do it, but there exist people who could do it. All right. Where are we? I mean, with a bike or a car, sure. Let's see here. After running at constant speed for exactly 27 minutes. All right, so all my runners look like this. I'm not sure why they're wearing a top hat for the running, but they are. Just accept it. Accept it. Where were we? So this is at 27 minutes. And I'm saying that over here is t equals to 0. And then what are we told here? There are still 1,200 meters to go. And over here we've got, what is this? Finish, right? Yay, finish. All right. The runner must then accelerate, at 0.2 meters per second squared for how many seconds in order to achieve the desired time? Ah, cool. So they've been, to start with what was going on, they were, I keep losing track of the problem. Which one was I looking at? I'm sorry, guys. 35. All right, so I hope you realize what I'm doing when I do. Who did I get this from? So when I try to solve a physics problem, here's my thought process. First of all, read the problem, right? Then second step is to, and this is actually could be done at the same time as I'm reading the problem. I make a picture and I try to write down all the information which I'm given and try to organize it and identify what I'm being asked, right? Now, in this problem, we're already, we know that the net distance is 10,000 meters, right? So you could figure out how far this runner has already run, right? What's that? Oh yeah, okay, great. Yeah, so we could figure that out. Does that matter to the problem? I'm not sure it does. Right? True? Great. But what are we asked? We're asked what acceleration is necessary in order that what? They meet the goal. What's the goal? to get to the finish line at what time? What's that? Less than 30 minutes. So if we're going to, you know, let's say let's say they do it just in time, right? Like every Hollywood movie ever made. So, you know, they reach the finish line at 30 minutes. That's the longest that they can take, right? So what's this mean? And are we told anything else that I didn't write down? Did they tell us what we have to accelerate at?
22 meters per second squared.
So we're going to accelerate at 0.2 meters per second squared for some time. Let me draw a picture of what's going on for a second here. I don't know if this is helpful or not. It may or may not be. What's going on here is, you know, the runner, if we're drawing velocity this way and time this way, here's a picture of what's going on. Up to time 27, I don't really know what's happening. I know that they start out with zero velocity because it's a race, right? And so they accelerate, and then whatever, they get to this point right here at 27 minutes. I don't know the details. I just know that after 27 minutes, they've run 8,800 meters. I could figure out the average velocity during that time period, right? 8,800 divided by 27, whatever that is, that's the average velocity, average speed for that first part. Then what we're told is that you're going to accelerate at 0.2 meters per second, which means that you're going to up your velocity for some amount of time, right? But maybe not the whole time, right? So there's some time here, let's say t1, right? And so if I said t1 is equal to, you know, like 27 plus delta t, this delta time, that's the speed up time that's necessary for the runner to get to that next speed, and then they're going to just be like plateauing out to 30 minutes. That's my reading of the problem, is because they're not going to accelerate all the way to the finish line. They're going to accelerate for a little bit, long enough that they can reach the finish line at 30 minutes. Yeah.
Wouldn't you need to find the average velocity of the last 3 minutes and then subtract that from the one that you get in the first 27 minutes in order to find the amount of time that you need to accelerate? So like finding the velocity.
You want to, what do you want to do again? You want to find the,
Finding the velocity of the first, what you were saying, the average of the
800
meters, and then for the last 1,200 meters, wouldn't you want to find the second velocity in order to make the time, or it could be?
I mean, perhaps, but we're kind of pigeonholed, if you will, because we're told that the acceleration is 0.2 meters per second squared, right? So we got to.
But wouldn't you take the relative velocity, subtract them, and then divide by the acceleration to get the amount of time you need?
Oh, I don't know about that.
Okay.
I'm not sure that's how it would work out. Maybe. Is what you guys have to speak up, because I. Well, we can't compare acceleration and velocity. I mean, it's accelerating, so she's going to speed up with this acceleration. Yeah.
You said finding the average velocity, and then it's saying that she's speeding up at the last, like in order to make the time. So wouldn't you do the average velocity minus the other like portion of the 3 minutes? Because in order to make it under 3 minutes, you have to.
Oh, you're thinking about the net average velocity? Yeah. Huh. Yeah. Yeah. Uh-huh.
What is the big picture of this? Like, what are we trying to figure out?
We're supposed to figure out what is delta t? Like the question is, how much time do they need to accelerate in order to make it to the finish line in time? Like how much time do they need to accelerate at 0.2 meters per second squared? If I understand the question correctly, and maybe I don't, because it seems kind of complicated to me at the moment, which makes me worry. I still don't understand what Megan's saying. Oh, wait a minute. See, I have not paid attention to something. We are told that what? What am I not using? Constant speed for exactly 27 minutes. That's important. So this is not that. This is wrong. It is, what it looks like here is magical. They start out running at full tilt and continue for 27 minutes. That's what's given to us. So in fact, we know, so probably what you're saying makes sense.
I just took that and divided, well, I did the amount of the distance divided by the time and got that velocity.
Okay. Well, I know a way to do it. Let me show you my way. And if you don't like my way, you might be able to do it Megan's way. I'm not sure. We'll see if the math bears it out. So what we know is that, so what you said the average speed over the purple part. What's the average speed here? So the average speed for the first 27 minutes would be 8,800 meters divided by 27 minutes, right? Meters per second. So 27 times 60 seconds, right? So how many meters per second did you get? Did you say? Oh, you said 5.5? Exactly 5.5? 5.43? All right, good enough for here. So that tells me that I know the initial velocity when they start accelerating, right? And all right, so here's the math of it. 8,800, let me try to organize my thoughts here. 8,800 meters plus, plus delta t times what? Oh, well. Curses. How to say this? Yeah, we're trying to find delta t. Well, I can say this much. Delta, I'm just going to write some things down. Sometimes you have to write things down with partial information and see how it works out. And then V average 2. And then plus 30 minus 27. Well, really, just 3. Let me get to the point here. 3 minus delta t times the second final velocity. So the VF2 is this velocity here, whatever that is. So this altogether, so I've got 8,800 meters to start with. Then I've got this acceleration phase, which has delta t time. There's some average velocity during that acceleration phase. And then I have the final velocity, whatever, we don't know that either yet. And that's all equal to what? What's this distance? This is the total distance, right? This together is 10,000 meters. Now, I don't know if that helps us or not, but that's true. Now, the V average 2, I can tell you more about that. That is the second final velocity minus, maybe this is what you're doing, Megan. It is Megan, right? Okay, good. This would, I mean, if it wasn't, I shouldn't have even asked. All right, let's see here. Oh, and then minus 5.43, right? Divided by, well, oh, I'm sorry, plus rather, divided by 2. Do you understand what I did there? So if we have, this is sometimes useful but often forgotten. If you want to calculate the average velocity, say from time 1 to time 2, right? And suppose this is V1 and this is V2. There's 2 different ways to calculate it. The one way to calculate the average velocity is by delta x over the change in time. But there's another way to calculate average velocity. The actual average in the sense of you give me both of your grades, I average them to get the average grade, that kind of average. So this is also equal to v1 plus v2 over 2. All right, so that's what I'm using right here. The average velocity over the delta t period would be the final velocity, vf2 as I'm calling it. It'd be vf2 plus the initial velocity, which we figured out is 5.43, divided by 2. That would be the velocity over that delta t time, right? So if I plug that up into here, then I have an equation that just involves delta t and vf2. So I've got still got two unknowns, right? What have I not used yet? Yeah, I've not used the acceleration. So how does that figure in? How does the acceleration figure into anything else? How about this? vf2 is equal to what? It's equal to 5.43 meters per second, right? Plus 0.2 meters per second squared times what? Yeah, times delta t. So at this point, we've solved the problem up to algebra, because all you have to do is take these two equations and shove them into there. You've got one equation and one unknown, so you can figure out the velocity, or figure out the time, whichever one you're after first. This problem's hard. But the way you solved it was easier, Megan?
I think so.
Did you get the answer in the back of the book? And would you like to share your way of thinking about it again? Now that I'm on board with what you're thinking, maybe?
So all I did was I started with 10,000 minus the 1,100.
Uh-huh.
Or mine was a little off, the 1,100 instead of the 1,200.
Okay.
And then I divided that by 27 minutes, converted that to meters per second, and got 5.5 or the 5.43. And then I did the 11,000 meters times, like I converted it.
You mean 1,100, but that's fine.
1,100,
Yeah.
yes. Trying to figure out what the speed
What the average,
was,
like
3 minutes.
the average speed for the last 3 minutes?
Yes, and I got 6.1 meters per second needed, and then I subtracted that by 5.5 and then divided by 0.2 because I used the equation acceleration equals delta v over t, and I did where t was equal to delta v over acceleration, and that's where I got 3 seconds.
So you've also assumed that the acceleration goes right up to the finish line. Yeah. So your interpretation of the problem is different than mine, but you got the right answer. So that's what the book wants. Yeah. I don't know, we should focus on other problems. This one is a little bit too complicated in my view. Yeah.
Where did the 1,100 come from when you were working?
She has a different version. She has a different version of the book. You have edition 6 or something, or is it edition 6 or something?
I just did it with the 1,200 and it comes out to that.
So what just if you couldn't understand what Megan was saying, what she's saying is that you want the average. I mean, you want it to take 30 minutes overall, and she's also assuming that there's a constant acceleration. My idea about the constant acceleration being just part of the final leg of the journey, no good, too complicated. The constant acceleration is over the whole final leg of the journey, and so you can figure out that the average velocity of the final leg of the journey has to be 1,200 divided by 3. 1,200 meters divided by 3 minutes, whatever that is, I guess 400 meters per minute. So that's the the average. And then so this is the average over the last part. But on the other hand, that is equal to what? It's equal to what?
It's about 6.67 meters per second.
Oh, did I do it wrong?
Well, you have to
Oh, you're converting to meters per second? Oh, okay. What was that?
That was about
6.67 meters per second? Okay. Now, why are you subtracting the other one? Final, so final, you're saying VF minus VI is what? Divided by what?
6.67 minus the 5.43.
Uh-huh.
And then dividing that by 0.2.
And-
The acceleration defines delta.
Oh, okay, so this gives you but why, what I don't understand is why would your final velocity be the average velocity of the last leg? That doesn't make sense to me because, and here's why. If we look at the velocity time graph under your setup, you got this 5.43 meters per second, right? And then at that 27-minute mark, you're constantly accelerating till the finish line, right? What's that look like? That looks like this in terms of a velocity graph. And so the average velocity over the final leg is like in here. So I don't understand why. Yeah? We only know constant acceleration. It's our only option. Or zero. I think we should move on past this problem. Yeah. Which other one you want? What else do you guys want to look at? Which one? All right. Let me pose a problem. Here's a problem. You have a car, all right, and it has some initial velocity v naught, and it has some final velocity vf, all right. And let's suppose that it constantly accelerates. Right, along this with acceleration a. So I'm not even posing a problem yet. I'm asking you, what equations of physics hold true for this situation? What equations can we write down? Suppose that the car is initially at position x equals to x naught. And suppose that this is the final position, x equals to xf. What equations hold true here? Let's also suppose it takes delta t time for this to happen. So let me just start writing down equations that are true for this. First of all, the final velocity is equal to the initial velocity plus the acceleration times the time elapsed. That's one thing we know. What else do we know? We also know that the final position would be equal to the initial position plus the initial velocity times the time elapsed plus 1/2 the acceleration times the time elapsed. So those are the kinematic equations for the velocity and also the position. What else? What other things do we know here? There are trickier things we know. Something else we know is that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the final minus the initial position. That last equation I wrote is the so-called timeless equation. This is only true for constant acceleration motion. Sometimes that's helpful to solve this sort of problem. Now, past this, there's more sneaky stuff, like we were just using for that rather horrible problem we were working on. One of the things is the average velocity. There's different ways of looking at the average velocity. One way would be if you were to draw the velocity time graph, what's it look like in this, guys? We start out with velocity v naught. We go to velocity vf. What's the slope of this line? If this is a vt graph. I mean, this is delta t. This right here, the rise over run is what? Vf minus v naught over delta t. What is this? This is acceleration, right? Now, that's not a new equation. We already had it at the top, right? Those are the same equations, just written in a different way, but that's sometimes an important way to look at it. But in this picture, you can sort of see what the average velocity is as well. It's like right here, right? So the average velocity is equal to 1/2 of the initial velocity plus the final velocity. This is also true. Yes, sir.
Would that acceleration be average acceleration technically,
We're constant acceleration, so the average is the acceleration.
Yeah, but if you just had that by itself, that would be considered average, but the average is the constant?
Yes. But we don't deal with, I don't know, acceleration's a constant, so you want to talk, what's the average of 3? I don't know, it's just 3, I mean, it's a constant. Yeah. But this average velocity, I'm saying it's 1/2 the sum of the initial and final, but we could also write xf minus x naught divided by delta t. That's another equation which is true. All right. So anyway, those are your main tools. So can you think of a word problem that I could give you in this world? How about this? Car travels 500 meters at constant acceleration, starting from dead stop. What is the acceleration A if motion took 10 seconds? Is that a question we can even ask? I mean, so you understand car at the start? What's the initial velocity? Initial velocity 0. 500 meter racetrack. It took how long? 10 seconds for it to get over here. I don't even know what the final velocity is, right? I know that if this is t equals to 0, I know that this is t equals to 10. What's my question? What's the acceleration A? Now, is there enough information to solve this problem? I hear no, I hear a yes. How would you do it? Yeah, we can put, it's our choice. We can make initial velocity, just initial position be 0, right? 500 meters is the distance, so if, the point is the change in x is 500, right? Now, what were you saying? What did you guys say? I'm sorry, I interrupted you. So that's 500. What else? Oh, okay. But we can solve that for A? Ah, very good. So this gives me 500 equals to, what's V naught? 0. So we've got 1/2 the A we don't know and the 10 seconds squared. We have a winner. That allows us to find the acceleration, doesn't it? Very good. So depending on how you package this question, you can get pigeonholed into either needing to use one or both of these equations, depending how the question's stated. You need to be aware of all of these tools at your disposal for constant acceleration problems, right? Now, the start of what we did today, did we need these formulas? No, because the problems I talked about at the start of today were constant velocity problems, right? For constant velocity problems, our main tools are just the concept of relative velocity and just velocity is equal to distance over time, right? Those are the main our go-to tools. Give me a second here, see if I can find a example for us. Do you guys have another question from the homework while I'm looking for something? No is fine.
I think so.
Okay. Yeah, you guys asked me the hard one. Ah. So, you know, I sent you a link. I sent you guys a link to, you know, my physics page, my physics 231 page. And if you look in there, I've got lecture 1, 2, 3, 4, lecture like all the way out to lecture 30 something posted, right? And you don't have to look at them, but they might be useful to you in places. When you're reading them, you just have to read them with a calculus filter, right? It's like, oh, calculus, ignore, right? So that will cut, for me, since I like to talk about calculus a lot, you may have noticed, my notes will shrink to about like maybe 2/3 at most of their length. But there's about 2/3 in there, which is just straight up college algebra-based physics anyway. And that's especially true of like lecture 3 on one-dimensional motion. I have some examples in there which would equally well apply to us. Maybe I should just project them. I think there's one in here I wanted to talk about with you guys, if I can find it. Oh man, it's not that one. It must be lecture 4. Oh yeah, lecture 4 is one-dimensional constant acceleration. That's actually got the Superman example in it on page 2, with different numbers and junk, but oh, calculus, don't look, it's hideous. All right. Here's a question. Suppose a car has brakes, which apply a constant deceleration of -2 meters per second squared. So let's say a constant acceleration of -2 meters per second squared. Anyway, if the car has an initial speed of 20 meters per second, then what's its stopping distance? That's a good question. That's a pretty typical kind of, I would say, you know, that question on a test is kind of a gift that we should all have a really good shot at solving that one. So here again, what's the initial velocity? What did I say? I can't even remember. 20 meters per second. And brakes. Brake, I can't spell brake. B-R-A, brakes apply a acceleration of -0. What meters per second squared? Oh, -2 meters per second squared. Pretty good brakes, right? Well, I don't know. That's only like 1/5 of gravity, right? If you really slam on the brakes in your car, you can, I think it's probably fair to say you feel like your whole weight sort of pressing forward, right? So I think good brakes might be able to apply an acceleration of at least like 1/2 g or something. I don't know. Probably depends on the road conditions, doesn't it? I mean, a brick wall will do better for you. But you don't want to do that. -2 meters per second squared. And the question is, what's the stopping distance? So what's the delta x here? How would you solve this problem? What's the right tool for this one? Now, we could certainly use the top 2 kinematic equations, which involve time, right? You can work with these equations and figure it out like that. But I'm telling you, this problem is tailor-made for this equation right here, because we don't care about time in this problem, right? So the question was, I forget, what's the stopping